Hello, friends. The universe is vast. So vast that sometimes when we think about it, it feels disappointing. Why? Because even if we discovered another Earth-like planet today with oceans and breathable air, it wouldn't matter. We simply couldn't reach it with today's technology. The scale of the universe. Our home galaxy, the Milky Way, is more than 100,000 light-years across. The nearest major galaxy, Andromeda, lies about 2.5 million light-years away. At the speed of our fastest spacecraft, roughly 28,000 kilometers per hour, that journey would take 94 billion years. That's far longer than the universe has existed. Even at the speed of light, the trip would still last 2.5 million years. So yes, the stars feel out of reach. Unless there's a shortcut. Wormholes, a cosmic shortcut. Imagine traveling to another galaxy in minutes. Not by moving faster than light, but by finding a tunnel through space-time. These tunnels are what physicists call wormholes. If you've seen Interstellar, you've seen the idea. Cooper's crew didn't fly across the universe. They slipped through a wormhole near Saturn and emerged in another galaxy. And this isn't just science fiction. Wormholes come straight from Einstein's theory of relativity. Einstein's space-time. In 1915, Albert Einstein published his general theory of relativity. Instead of describing gravity as a force, Einstein revealed that massive objects bend space-time itself. Picture space-time as a rubber sheet. Put a heavy ball on it, and the sheet curves. Smaller balls roll toward it. That's gravity, not a force, but geometry. Einstein's field equations describe how matter curves space-time. Out of these equations came predictions. Black holes, where space-time bends so much that nothing can escape. And wormholes, bridges through space-time. Black holes and bridges. In 1916, Carl Schwarzschild found the first solution, black holes. 2 decades later, Einstein and his student Nathan Rosen found another, bridges linking separate regions of space-time. They called it the Einstein-Rosen bridge. Today, we call it a wormhole, visualizing a wormhole. Here's a simple way to see it. Draw 2 points, A and B, on a sheet of paper. The shortest path is a straight line. But fold the paper until A and B touch, and suddenly they're side by side. Punch a hole through, and you've created a shortcut. That's a wormhole, a tunnel folding space-time. John Wheeler and the wormhole. The actual term wormhole was coined in 1957 by physicist John Wheeler. He compared it to a worm burrowing through an apple. Instead of crawling across the surface, the worm cuts straight through. That's exactly what a wormhole would be, a cosmic tunnel. White holes, the other side. But if a wormhole has an entrance, what about the exit? If the entrance is a black hole, a place where everything falls in, the exit must be something different. Physicists call it a white hole. A white hole is like a black hole in reverse. Nothing can enter, but light and matter can come out. In theory, a black hole and a white hole could form 2 ends of a wormhole. Do white holes exist? So far, white holes are only theoretical. The idea was proposed by Russian physicist Igor Novikov in 1964. Some suggest the Big Bang itself might have been a white hole, an event where matter suddenly burst into existence. Others, like Stephen Hawking, speculated that when black holes die through Hawking radiation, they might leave behind white holes. In 2006, astronomers saw a strange gamma-ray burst, GRB 060614, that didn't match known patterns. Some wondered, could it have been a white hole? No evidence yet, but the possibility remains fascinating. The problems with wormholes. As exciting as wormholes sound, they face major challenges. 1. Instability. Wormholes collapse almost instantly. The moment something enters, the tunnel pinches shut. 2. Exotic matter. To keep them open, we'd need negative energy, a type of matter that pushes instead of pulls. We don't know how to make it. 3. paradoxes. If wormholes connect not just space but time, they could allow time travel. That means paradoxes like altering the past, which physics might forbid. So yes, wormholes are possible on paper, but maybe not in practice. Wormholes in the lab. Interestingly, in 2015, scientists created a kind of wormhole, not in space-time, but in magnetism. Using superconducting materials, they built a device where a magnetic field vanished at one end and reappeared at another, as if it had traveled through a tunnel. Of course, it's not a real space-time wormhole, but it shows how the concept can inspire real-world experiments. Warp drives. Another shortcut. If wormholes don't work, could we still go faster than light? In 1994, physicist Miguel Alcubierre proposed the Alcubierre drive. The idea, don't move the ship faster than light. Instead, warp space-time itself. Contract space in front, expand it behind, and the ship rides a bubble. This doesn't break relativity because the ship never moves faster than light. Space does. The catch? Again, it requires negative energy, and lots of it, far more than we can produce. Why wormholes inspire us. So why do we keep dreaming about wormholes, even if they may never exist? Because they represent freedom. The freedom to escape distance, to reach the stars, to bend time itself. A century ago, black holes were just equations. Today, we've photographed one. Who's to say wormholes, or even white holes, won't one day leap from theory into reality? Closing scene, stars fade into darkness. Until then, wormholes remain one of the most fascinating ideas in physics, an invitation to imagine what lies beyond the limits of distance, time, and maybe even reality itself. Thanks for watching. Please like, share, and subscribe.